All right, everyone. Welcome back to session 2 of Runtime School. So today, the last time we talked a lot about how the runtime bootstraps itself and gets started. And I'm actually going to try and start somewhere not too far from where we started or from one of the things that we did right at the end of the last session. Before I begin, are there any questions that people wanted to ask in person from the last session to clarify any of the details that we talked about the last time? That maybe you had some time to look over the code in more detail since then? Nope. Okay, I will keep going. You can interrupt me at any time and tell me to stop, and I can answer questions. Okay, so what I want to begin today doing is actually looking at what we think of as the operational pipeline for how tasks and other operations are executed as part of running Legion programs. So you'll recall that we have a separate runtime object that exists on every one of our nodes that we looked at how they get created the last time. And so each one of these runtimes is responsible for executing tasks. And every one of these tasks has the potential to go and launch sub-operations. And these sub-operations can be other tasks, or they can be things like inline mappings or explicit region-to-region copies or so forth. And we're going to see there exists a whole bunch of different operations that these subtasks can launch. And one of the main functions of the runtime object on each one of these different nodes is to actually provide a pipeline for executing all of these different operations that can be launched. So today what I want to do is look at the structure of what some of those, of how that pipeline works, so that we can see, sort of how the runtime manages the execution of these operations. I'm not going to go into detail today about what all these different operations are. We're going to do that in a later session. But what I want to do today is look mainly at this pipeline and how it operates. And what you're going to see is there's a very nice abstraction for this function class and how it progresses through these through the pipeline maintained by the Legion runtime. Okay, so let's start somewhere where we actually, from some place that we actually looked at the last time. So I'm going to go here into runtime.cc, which is a file that we spent a fair amount of time in the last time. So you recall that, let's go look at the code that launches the top level task again. We looked at this very briefly last time that we met. So I'm searching for, let's see if I can remember what it was. Launch top level task. Here's our function. Oh, went too far. So here's our function, launch top level task, that is responsible for launching one task on one of our processors somewhere inside of the machine. And you recall that we create this task launcher object, we create an individual task. We create a task launcher to initialize this top level task. We set a bunch of parameters based on the inputs, copying in command line arguments and stuff like that. And eventually we get down here to this call right here that says add to ready queue. And this call add to ready queue is the entry point to the Legion operation pipeline. So let's actually see. So what we're going to do today is we're actually going to just try and trace through an operation that actually goes through the Legion pipeline. So let's actually see where this add to ready queue call goes to. This is where we're moving into new territory. And I think I need to add 2 semicolons here to make sure we get the actual. Let's see. Am I doing something wrong? Ready queue. There are a bunch of different invocations of this method. Let's see if I can find the right one that I'm actually looking for. Go. Went too far. So this is the runtime call for add to ready queue. So you'll notice that it takes arguments. One saying the processor that we want to add this task this queue to the pipeline for. We get a task operation that we're going to add onto this ready queue, and then we say whether or not this operation has failed, mappings or anything else other time in the future. For the moment, you can just assume that this previous fail is always going to be false, and that things are being added to this pipeline for the first time. So when the runtime gets one of these calls to add ready queue, the first thing it does is it's going to go and put this task in the list of operations that need to have their dependence analysis done for actually going about and executing these operations. So the first thing we do is the runtime maintains what we call a bunch of different objects called processor managers. And these processor managers, there's one processor manager for every low-level runtime processor that is not a utility processor. And the idea is that once a task is ready to run, we can go ahead and add it to one of these processor managers. So we can actually go and see what these processor managers look like. So let me find or let's actually go and see where this add to ready queue goes on the processor manager. So I'm actually can search for the same. It's actually the same method name. It's just going to be on a processor manager object. So these processor manager objects exist for every one of our low-level runtime processors. We make one in the high-level runtime to store metadata about all the different processors and all the things they have to do. And so you can see when we get one of these calls, we actually go and enqueue this operation on a list of ready queues that are ready to have operations which are ready to actually be executed. So before, when I told you that this was the beginning of the pipeline, I actually realized that I just lied. This is actually, we actually get to skip a step for the top level task. And I'm going to step that we skipped right now because it's a very important step and it's really the actual beginning of the pipeline. So this add to ready queue implies that this operation is actually ready to be executed. And you recall, from the Legion programming model that operations are responsible for doing their own, or the Legion runtime are responsible for doing the dependence analysis for our different operations that are launched based on the region requirements that different operations specify. So it's up to the Legion runtime to figure out which operations can run in parallel and which ones have to actually be serialized because they have data dependencies based on their region requirements. There's actually a stage that comes before this add to ready queue. The ready queue implies that all of our dependencies have actually been satisfied. And for the top level tasks, it's okay for us to assume that all of our dependencies have been satisfied because there's no operations that came before the top level task. So we don't actually have to do dependence analysis for the top level task. So we're effectively skipping a step for that particular task. However, most operations, the actual beginning of the pipeline begins with a call that comes to before add to ready queue, which is add to dependence queue. So let's actually show you, where one of these calls comes. And I'm actually going to show you a call that comes in the Legion runtime that everyone who's written a Legion program should be familiar with, and we'll see how we enter this Legion pipeline. So let's actually search for the call that executes a single task. So I'm going to search for runtime execute task. So everyone that's written a Legion, let's actually get one with the launcher here. Here we go. So everyone that's has written a Legion program has probably launched a single task operation at some point. And this is where that call enters the runtime. And what you'll notice is that there's a bunch of different things here that go on in order to check to see if, for example, if we predicated our operation false, we can skip a whole bunch of steps. But at some point down here, if we're not predicating false, what we do is we grab a new individual task operation. We're going to see that this individual task class is a subtype of the class that we're going to look at today. So this is just a special kind of operation that we're going to execute. What we do is we initialize this task object based on its launcher. We get back the future result that we're going to return, and then we're going to go through some code to execute to actually launch the task. I'm going to go through this execute task launch call here just at a very high level. We'll come back to it in another session to look at it in some more detail. But what I want to show you is the entry point to the Legion pipeline. So let's actually search for this execute task launch method. Okay, here we are. There's a whole bunch of things that go on in here to figure out, are we inlining this task? Do we have any mapped regions that we need to unmap in order to avoid deadlocks and stuff? And I'm going to skip all of that logic for today. But what you'll notice is that once we've actually done everything, we actually have this call here which says, add this task to the dependence queue. And this add to dependence queue is the actual entry point to the pipeline. So where I lied before and told you that add to ready queue is the entry point, add to dependence queue is the actual entry point to the Legion task pipeline. Let's actually see where this goes. And we're going to see it goes right back to those processor manager objects that we've looked at very briefly before. And we're going to go right back there. So let's search for add to dependence queue. So this is the runtime call to add to dependence queue. You'll see it's right above the add to ready queue call. It does something very similar, which is it looks up the processor manager that's going to be responsible for executing this operation. Notice here that our argument here can be any operation that can be passed into this dependence queue. We're going to look up the processor manager for the processor that we're running on, and then we're going to go and put this operation in the list of operations which need to perform dependence analysis. Let's actually see what happens when we look for add to dependence queue. I'm searching for add to dependence queue. Here's our call for the processor manager to add this operation to the list of operations that need to perform their dependence analysis. You'll notice what we do is we actually we end up this processor manager has a bunch of data structures for tracking all the different operations in different stages of the operation pipeline. And we're going to look at operation managers in a little more detail later today. But what you're going to see is that we're going to launch off a meta task onto one of our utility processors here, which is going to be responsible for doing the actual dependence analysis. So the way we do this is we build up a little struct here that says, what the arguments are for this meta task. We give it a task ID, which is the high-level trigger dependence ID. We're going to give the manager, which is responsible for doing the dependence analysis. Here's the operation that we're going to actually perform the dependence analysis on. And then we're going to get the context ID for the parent context. These are just basic arguments or the context ID we're going to need down here to update the preconditions. Do you recall that dependence analysis is actually a serial process? And so what we do is every processor manager for every context which is executing, and you think of a context as just some task that's running somewhere on some processor, we have a different context for every one of those tasks. And all the operations which get generated inside of these tasks have to perform their dependence analysis in program order in order to figure out correctly what dependencies exist between them. So every processor manager knows which contexts are executing on its processor, and it keeps track of which of the event for the previous operation that executed, or the dependence analysis for the previous operation that was executed. So this little dependence preconditions, let me actually show you where that is so you can see what the data structure looks like. So I'm going to jump back here to runtime.h. I'm going to search for the class processor manager. Here's our processor manager class. It has a whole bunch of stuff in it today, which I'm not going to talk about in a lot of detail. But I'm going to find this dependence analysis preconditions. And so what you see right here is that really all this is just a vector of events indexed by a context ID, which says, this was the previous event for this previous metatask for the dependence analysis for the previous operation that was launched in the pipeline. So this is the event that will trigger, the low-level runtime event that will trigger when the metatask from the previous dependence analysis actually completed. And you'll also notice we keep a little reservation here, which is used to protect this data structure. And that's because there can possibly be different people launching these events. So we need to, or from different contexts. And so we need to have a way of locking this vector just in case it gets resized or something like that. Okay, so let's jump back to where we were before. So we're going to jump back to runtime.cc. I'm going to search for add to dependence queue again. Okay. So what you see is that what we're doing here is we're launching off a low-level runtime event onto a utility processor for this processor manager. So this utility processor is a low-level runtime processor, which has been designated as one of our CPUs for doing meta runtime work for the Legion runtime. And we're spawning off a special task, the high-level runtime task ID, that's going to say this is a meta task that our high-level runtime is going to execute. We're passing in a pointer to our args data structure, which we filled in with the information about what this meta task needs to do. We need to pass in the size of the args, and then we're passing an event precondition here, which is saying, you can't run this meta analysis until this dependence analysis until the dependence analysis from the previous operation in the same task context has been launched. And we get back a new event from the low runtime that says when this dependence analysis is going to finish. And we put this back into the data structure, the dependence precondition data structure, to say, for the next operation that comes along, this is the event that you have to wait on before you can actually run your dependence analysis. And you'll notice that all of this is protected with the access to this dependence lock. This auto is just a helper utility structure which locks the dependence lock here as soon as it goes onto the stack, and then as soon as it gets popped off the stack, the destructor will go and unlock that lock for us. You'll notice that Sean and I use these auto lock helper objects a lot in our code. They're very nice because you never have to worry about missing locks and unlocks. You make sure you get good pairing and stuff like that. Okay, let's actually see where this meta task comes out, and we'll actually see a little bit about how, and then we're going to jump into how the pipeline actually executes. Okay, so this high-level runtime task ID is one of the 3 special tasks that the high-level runtime registers with the low-level runtime as something as one of our special task IDs that we're actually going to run. So I'm just going to show you the registration for this high-level runtime task ID actually occurs in the same place that the initialization task that we looked at the last time is registered. So let's see if I can actually find this pretty easily. Let's do a search here for register runtime tasks. I remember why this is a difficult one to find. There's no colons on the front of it. I'm searching for register runtime tasks. So here we can see this high-level runtime task ID. Remember, this function, register runtime tasks, is called at startup time as part of the initialization of the runtime. The last time we looked at where this initialize runtime method call gets used. And today we'll look just very briefly at where this high-level runtime task actually gets called. So if we look for, so every time that we pass a low-level task with this high-level runtime task ID, we're going to end up invoking this function, which is the high-level runtime task. And this is our generic meta function for the high-level runtime. So let's actually find this task. For a high-level task. And you'll notice it's all the way down here at the bottom of runtime.cc. And notice, it gets all the arguments that a low-level runtime task assumes. It gets a set of arguments, the arg length, and the processor on which it's running. What you'll notice is that this high-level runtime task actually handles a whole bunch of different kinds of tasks for the high-level runtime. There's all sorts of things that go on in here for doing, deferred dependence analysis and deferred execution and deferred mapping and all sorts of different things. And you're going to see where you'll reuse this task over and over again today. But what we want to look for is, let's actually go back and look at where we launched this high-level task, or this runtime meta task, and we'll see where we get this ID from. So if we search for, if we go back to add to dependence queue, here we go. You'll notice that the first thing we put in our arguments for this high-level runtime meta task was this high-level runtime trigger dependence ID, which is effectively the name for what we want our high-level run, or the command for what we want our high-level runtime meta task to actually do. So let's actually search for this. You're going to see it only shows up down here at the bottom in the actual implementation of the high-level runtime task. If I can spell correctly, dependence ID. Okay, you see that it ends up as being one of the cases inside of this high-level runtime task. When we switch on the task ID, the high-level runtime task ID that we're supposed to do, you'll see that we'll end up in this block right here, which is high-level runtime trigger dependence ID. At this point, we can cast our arguments back to the right kind of arguments, and then we can actually pull out the operation right here off of our arguments that we actually want to perform our dependence analysis on. And we're going to call this method on this operation called trigger dependence analysis. And this is where operations actually start progressing through the pipeline. So let's actually look at this operation class in more detail, and that's what I want to spend the most of our time on for the remainder of today. So sort of giving you some feel for how the runtime starts progressing operations through the pipeline, and now I actually want to look at this operation class in more detail. So I'm going to jump back out of this file. And I'm going to scroll up here to the Legion ops.h header file. So everything involving operations in Legion will be done will be declared inside this Legion ops header file and then implemented inside of Legion ops.cc. The one exception to this, of course, is that Legion tasks, which are a special kind of operation, have their own header file and own implementation file. And we'll, of course, be looking at those in more detail a lot later. But what I'm going to do today is we're actually going to look at this generic operation class, and we're going to trace through how it works. So I'm opening up Legion ops.h. And the first thing that you're going to see here at the top of this file here is this class operation. And you'll notice the comment for this, is very indicative of what this class is doing. So this operation class is serving as the root type, the base type of a tree of types for all the operations that can be created in a Legion program. So every one of our operations that we run through this pipeline has to inherit somehow from this operation class. Just to give you an example, so this operation class, just to show you some of the things that inherit from it, if we search for public operation for doing public inheritance, we notice we have a predicated class that can, any operation which is going to be predicated inherits from this operation. Speculative operations inherit from operation. Fences, frames, deletions, flows operations, must epoch ops, etc. There's other operations in here also that inherit from some of these other intermediate classes, and we'll go into those in more detail later. But up here at the top, this operation class is really the basis of all the things that go on inside of Legion. So every time we want to add a new operation to Legion, we end up extending this operation class. And just to give you an example, we actually have a couple of operations which are currently pending inside of Legion. For example, we're going to be adding some new dependent partitioning operations, which allow our partitionings to be deferred based on some data inside of regions. And so these new, partitioning operations are just going to extend this operation class, just like all the other operations that we have inside of Legion. So let's actually find that call that we did from our high-level runtime meta task. I think it was perform. Let's see. There's something dependence analysis. Here we go. Trigger dependence analysis. So what we'll see is I've actually gone too far here. Let's actually search from it starting at the top. Trigger dependence analysis. Actually jumping too far here. Let's actually start from the top. Here we go. So I'm back here in the operation class. You'll notice this operation class has a bunch of different stuff in it. But the main thing that it has are a whole bunch of virtual methods here. We want this class to be extended for all the different kinds of operations that we're going to launch inside of Legion. So what we do is we provide a whole bunch of virtual methods for all of the different stages of things that can occur inside of the Legion, for all the different stages of an operation progressing through the Legion pipeline. So the first one, and these virtual methods pretty much come in order. So the first call is obviously to call trigger dependence analysis. And the way to think about each of these operations is that they're going to be invoked by the runtime, and it's up to the operation class to provide an implementation of each of these different operations. So when we call trigger dependence analysis, we're going to have to do something for this operation in order to figure out what our dependencies are on all the operations that came before us. When we get called to trigger our mapping, we're actually going to have to do the mapping for this operation. When we call trigger execution, our operation is going to actually have to launch itself onto the runtime. Trigger resolution is for resolving speculation, and then we have doing triggering complete and triggering commit. I'm going to skip deferred complete and this report alias requirements. They're special cases for certain kinds of operations, and in most cases they end up being no ops for a lot of these operations. But really, everything that starts with trigger is an action that's going to be invoked by the high-level runtime, and it's up to the operation class to provide an implementation of these different functions. Now, the cool thing about this is that you'll notice that these are not pure virtual functions. So effectively, there are a couple pure virtual functions in this operation class, but they're pretty generic. Things like activating and deactivating and getting a logging name for logging operations. But pretty much all of these operations that begin with trigger have default implementations. So when you extend this operation class, you're immediately going to have an operation which can progress through all the stages of the Legion pipeline correctly. And we're actually going to go take a look at each of these operations, or each of these trigger calls. And the cool thing is that you could effectively, the first time you extend this operation class, you're effectively just making a no-op until you actually modify these virtual methods. So any operation that you make will immediately be valid and be able to progress through the Legion runtime pipeline with no trouble. And you just really have to modify these calls where you want to in order to get the desired effect for the operation that you actually want to create. So let's actually go look at the implementation of some of these trigger calls in more detail. And we'll come back to this to some of the other methods up here in this this operation class in just a little bit. So I'm moving back out. We're going to go look in Legion ops.cc for the implementation of these different trigger calls. So I'm going to search for trigger dependence analysis. I can spell again. Here we go. Oh, I went too far again. Search function is being pedantic on me. So we search for trigger dependence analysis. Okay, here's the base operation class for dependence analysis. You'll notice it does two things. It calls begin dependence analysis and then it calls end dependence analysis because the base operation class doesn't have anything to do dependence analysis on. It doesn't have any region requirements, so it's not going to have any data dependencies on anything that came before it. We'll actually go look at some of these implementations of begin dependence analysis and end dependence analysis a little later when we actually start talking about how dependence analysis works. But effectively, every operation should just call begin dependence analysis before it does anything, and then when it's done, it calls end dependence analysis. And what we'll see is if we look at other operations, they'll have stuff in between these calls to actually do some of their dependence analysis. And just to give you an example, if we actually look at the inline mapping operation, which is a map op, and we search for trigger dependence analysis, what you'll notice here is that there's some logging calls here, but then what we get is we get begin dependence analysis. We then actually perform some dependence analysis on our one region requirement that we have for our inline mapping, and then we call end dependence analysis. So you'll see that pretty much every one of the operations that actually needs to do dependence analysis follows all this same approach of calling begin dependence analysis, doing something, and then calling end dependence analysis. So we'll go back to operation, trigger dependence analysis. Right, so this is trigger dependence analysis. Let's actually look at some of the other calls here. So the next one of our trigger calls here is actually say trigger mapping. And what this is going to do is actually going to put our operation on a list of queues that inside of our processor managers. So we're calling back to our high-level runtime instance here. And we're calling add to local queue, which says that this operation is ready to execute. We'll see a little bit later that the local queue and the ready queue that we saw earlier for our top-level task are actually just two variants of the same thing. One is for tasks and one is for generic operations. But they both go to the same place. They both go to those processor managers, which are responsible for actually executing the operations once they're ready. Our next call here is trigger execution. So trigger execution is a little bit special. You'll notice that unlike the previous two calls, trigger execution actually has a Boolean return type, which says whether or not the operation successfully triggered. And there are cases where it might not possibly succeed when it triggers. For example, if it fails to map, if there aren't enough resources for the operation to actually map at the current time, it can return false. And that will, cause the operation the Legion runtime to push it back onto the list of things that are ready to do, but are not quite that need to have this trigger execution method invoked again. Now you'll notice that this trigger execution call right now calls two sub methods inside of this operation class. It calls complete mapping and then it calls complete execution. So the interesting thing about each of these stages inside of this operation class is that you can actually defer them for any arbitrary amount of time. So just because your function returns doesn't mean that the operation actually assumes that the stage is actually completed. So just because you exit one of these trigger calls, so for example, inside of trigger dependence analysis, that doesn't automatically assume, the runtime doesn't automatically assume that you've finished that stage. You actually have to do something to end that stage. And it turns out that doing something is handled by some of the basis of the operation class. In the case of things like trigger execution, actually finishing the execution stage involves, calling complete mapping and calling complete execution. But let's say, for example, you actually wanted to, wait until you've actually finished running some operation until later to actually mark that you finished the execution stage of the pipeline for this operation. Well, then you don't actually need to call complete execution now. You might, go off and do something, launch some more low-level runtime tasks, and at some later point call complete execution. And the cool thing is the operation class abstracts all the details of this operation logic so that you don't need to worry about that. You can actually defer the completion of this execution stage until you're ready and actually call completion later. And it turns out this style of programming has a name. It's called event-driven programming. And the idea is that, effectively, when this operation class gets invoked with trigger execution or any one of these trigger methods, it's effectively getting a notification that it needs to do something. And then when it's done, it calls some other method that says that it's actually finished handling that event. And so the nice thing about this is that I've abstracted all the details about what's actually going on in the logic of this operation class behind all of these calls, so that we don't need to duplicate it and replicate it across all of the different operation classes that we end up implementing. You'll notice there's some other trigger calls here. So for example, there's trigger resolution, and we're done, resolving any speculative operations. We can call resolve speculation. And we get similar things for completion and commit for our pipelines. So trigger complete, we have a similar complete operation, and then trigger commit, we call commit operation. So the interesting thing about all these different calls is that there's actually a lot of logic that goes on inside of these operations for the operation pipeline. So if you think about how the analogy here that you should keep in mind when thinking about these operations is that very similar to how out-of-order processors process instructions. These operations are progressing through these different stages of triggering. Effectively, these different trigger calls represent different stages in the pipeline that they need to be executed. And then when we're done with each of the stages, we call the method saying we're done, and we can progress to the next pipeline stage. The one variation on this is that we actually don't need to do, some of these stages do not have fixed orders. So certain things like dependence analysis always has to come first, and then we always have to map, and then we always have to execute. But some things like trigger resolution can actually occur out of order with respect to some of these other stages. So for example, once you've mapped, you've actually most likely resolved, it's possible you may have resolved your speculation prior to actually needing to map and execute. So there are cases where some of these stages can actually be done out of order. And again, the cool part about abstracting all this behind this operation class is that all of this logic is already baked into the basis of this operation class in more detail. And you don't need to understand all that in order to inherit from this operation class and use it to create new operations for Legion to actually execute. Okay, so this is all very abstract. So what I want to do is actually dig into some more detail about and actually walk through an example of what some of these things so how some of this logic works for this operation class that we can investigate it in some more detail. So let me actually jump back here for just a moment, and we're going to come back into this Legion Ops class here very soon. So if we go back and look at legionops.h, I'm going to scroll down here. Here's all our virtual trigger methods that we were looking at before that say, these are the different stages, and they're going to get triggered by the runtime. And you'll notice that right down here below all these trigger calls are the corresponding, complete and resolve and commit operations that you call in conjunction with each of these virtual methods once you're actually done handling your process for actually executing, for performing each of these trigger operations. So what I want to do is actually go and look at what the implementation of some of these mapping and execution calls how they're actually implemented, so you can see what they're actually doing. Let's jump back to legionops.cc. We're going to search for complete execution. So what you'll see is that this complete execution call has, this is what we're going to call at the end of every operation as soon as we're done actually executing this. And what you'll see is that there's a whole bunch of variables that were or state variables inside of this operation class that we update. So what we're going to do, just to give you an example of, just to walk through some of what's going on here. These are just variables we're putting on the stack. We'll see what we need them for in a minute. I'm going to skip this part right here for right now. Notice we build a little scope right here so that we can use our auto lock object here to take our lock on our particular local operation. We have a state variable that marks whether or not this operation has actually executed or not, has it progressed through the execution stage. When we do, we're going to mark that this operation has actually executed. And then what we're going to do is we're going to check to see if we need to perform any additional operations now that we've actually finished this stage of the pipeline. There's a whole bunch of logic going on here. So for example, we're going to check to see if we've mapped, if we haven't resolved, if we have any outstanding speculation dependencies, previous operations that we depend on that are still speculative, and whether or not we've invoked our trigger, the resolution method. If any of these cases are true, we're going to mark that we need to trigger our resolution. So this need resolution variable is going to get marked right here as being true. And you'll notice that after we release the lock here, notice the scope ends right here. So our lock will go out, our auto lock object will go out of scope. And then after we've released that lock, we can actually do the triggering of the resolution. And notice that this trigger resolution call here is one of those trigger operations that gets invoked by the runtime whenever as operations progress through the pipeline. So there's actually logic like this in each of these different complete operations. And you'll notice they're all similar. They're all similar in some way. So here's the one for complete mapping. Again, we put some variables on the stack saying whether we need to do any operations when we're done. We take our lock for our operation. There's a whole bunch of we mark that we've completed our mapping. And then there's a bunch of logic here that figures out the various stages of our pipeline and what needs to be triggered after we're done releasing our lock. And this is true for complete. This was complete mapping right here. This is complete execution that we looked at before. There are ones for resolve speculation. There's one for complete operation, and there are ones for commit operation. Now the cool thing is that there's a lot of complex logic here, and there's a lot of very nasty race conditions that took a while to get right. But there's a lot of it, but it's effectively correct now, and it should be correct for all operations that we're ever going to need to use in the future. So unless the Legion pipeline changes in any measurable way in the future, we shouldn't have to modify any of this code. So if you ever find yourself trying to modify any of these complete or resolve or commit operations that you call after inside of the trigger operations, you're probably doing something wrong. I'm not going to go into a lot of detail into this logic because it's pretty complex and it would take me a lot of time to actually jump through in a lot of detail. But what I want to do, so unless people have questions about it, I'm happy to answer them. But unless people really want to hear about what goes on inside of this logic, I'm probably going to skip some of it. Any comments? Okay, I'm going to keep going. Okay, so let's jump back to this Legion Ops class.h just to show you some of the state that the Legion Ops class actually keeps. So we have, let's see, this is our operation class. We have all of our trigger methods. Here are the complete, resolve, more complete, and commit operations. Notice, by the way, that these methods are not virtual. And that's, again, designed intentionally because I don't want you overriding those in any of your derived classes. You can override these, but you just end up needing to call the right variations of these operations inside of the base operation class. So if I scroll down here a little bit, down to the bottom of this operation class, you'll notice that there's a whole bunch of state information. This is where we're keeping all of our state information for our operation. So we're tracking whether it's mapped, executed, resolved, whether or not it's been hardened for resilience, completed, committed, and then we also track whether or not some of our operations have some of our trigger operations have already been invoked. And these are all necessary for avoiding race conditions and other things that can occur in this event-driven programming approach. Okay, so let's see. What is the natural thing to do to look at next after looking at some of these things? I suppose the best thing to do is actually to continue to walk through this operation class just to show you how the no-op version of this operation class would proceed through this pipeline. Let's go back to legionops.cc. So if we look for, we were looking at trigger dependence analysis before, or trigger dependence analysis. So notice that we called begin dependence analysis and end dependence analysis. We can actually go look at these real quick and see what happens when we call these, when these things are actually called. So we look at begin dependence analysis. You'll notice that what we do is we add a couple of initial sort of placeholder references onto our outstanding mapping dependencies. These are operations references that we need to wait for before we can actually start mapping. And these are references that we need to wait for before we can resolve our speculation. We do some operations based on our parent task, and then we're pretty much done. There's not a whole lot that goes on here. And then you'll notice that right below begin dependence analysis here, there's the end dependence analysis call. And you'll notice the first thing we do here is we take our lock. We have to do this because, at some point, once we've registered dependencies, we might start getting calls to decrement the number of, say, outstanding mapping dependencies that we have. In order to do that safely, we have to be holding our lock because these references from other operations which are triggering and marking that they're done mapping. So we have to decrement these sort of placeholder references that we added in begin mapping dependence up here. These are literally just, these were trying to make sure we didn't trigger prematurely. So we added an extra mapping dependence and extra speculation dependence. Yeah, go ahead.
So when you increment that outstanding mapping depths variable, how is that safe without a lock?
It's safe here because we see the comment right above it. It's safe to do that without the lock because nobody else has a reference to us yet. We haven't actually done any operations to register any mapping dependencies yet.
Okay,
and so
but
no
it's
one
not
is
an
going.
atomic or
it's
anything.
not atomic.
Fancy.
No, it's not atomic in any way. But we don't need to hold the lock because no one else has. We haven't registered any dependencies yet, and so no one is going to be touching that variable yet.
Mutual exclusion through obscurity.
Exactly. Yes.
Okay.
Exactly. So it's safe up here, but once you get down here into end dependence analysis, now you have to take this lock to be safe. So we remove these sort of placeholder references just to prevent premature triggering. And then we can go through and start checking our conditions for what we need to do. And the one that, is most likely is the actual, let's see if we can find the one that I'm actually interested in. Okay, so I believe the interesting one is if we've actually already satisfied all of our mapping dependencies. So we would enter this case where we're not mapped. All of our outstanding mapping dependencies are 0, and we haven't invoked the trigger mapping yet. We're going to mark that we're going to invoke it. We've marked that we're going to need our map to be triggered. And what you'll notice down here is that we have our special case here if we need our mapping. Let's see. And I'm actually remembering some of this logic myself right now. You can tell it's very complex logic. There's lots of different cases going on here. And there are lots of nasty race conditions that took a long time to get right. Right, so one of the things that we can do here is we can figure out, I'm going to ignore this dependent children, whether or not our dependent children have been mapped condition for right now. We'll just assume that it's empty. We'll just assume that it's empty for right now. And yes, this is some complex logic. I've clearly forgotten it all. Yes. So here we go. So if we've actually satisfied all of our mapping, we don't have any dependent. If we don't have any dependent children, we can skip this else statement here, so we can do trigger now. And if we hit trigger now, and we don't have some other conditions, involving must epic launches and stuff, we can actually invoke the trigger mapping method right away. So it's possible, in our no-op operation, we effectively don't register any dependencies. We don't have any of these other nasty conditions that can occur for having sub-operations or must epic launches or anything, so we can actually invoke our trigger mapping operation right away. So let's jump back to the trigger mapping operation for the operation class. Mapping. What you'll notice is that this makes a call to the runtime to add this this processor to, or add this operation to our local queue. So let's actually jump back to the runtime and see where that goes. Jump back to runtime.cc. Search for add to local queue. So we notice we grab our processor manager, we call add to local ready queue. Add to local ready queue. What you'll notice is that the processor manager does something very simple. What it does is it says, I'm going to launch a new meta task. So again, anytime you see this, this pattern here of declaring some arguments, and you see one of these HLR underscore something, that's an indication that we're going to launch a new runtime meta task to actually do an operation. And what we're going to do is we're actually going to launch this operation contingent on having a set of waiting for any operations that were launched before this to map inside of our local processor manager. This is mainly just to avoid dumping too many operations onto the local runtime at one time. We're going to defer it based on the event waiting for the previous operation that actually was launched onto the local runtime meta task or utility processor here. You'll notice that we just take a little lock on our local ready queue. We get the event for the precondition. We set up our arguments for launching this trigger op ID meta task, and then we launch our little meta task on the utility processor. We get an event next, and we can add that back onto the list of things to do. So let's actually see where this high-level runtime meta task comes out. So if we search for the high-level runtime task ID, we should see this down here at the bottom of runtime.h. You'll see this is the second one of these that we've looked at today. So we look for trigger op. We notice that here's our trigger op case. Notice we're back here in high-level runtime task, our high-level runtime meta task handler. So when we break on, or when we switch on the task ID, we end up here in this high-level trigger op ID. We pop off our information, so we get our operation too, and then we end up calling trigger execution on this operation. When we call trigger execution, we're going to jump back into legionops.h, and we'll look at this trigger ops implementation for the low level, or for the base operation class. So I'm back in legionops.cc. We search for operation trigger execution. We notice that we don't actually do anything. We don't actually have anything to execute because this is the base operation class. So we call complete mapping, which is going to mark that we've finished our mapping, and we're going to call complete execution. Let's actually look at complete execution just in a little bit of detail. We go to complete execution. At this point, you recall we already called that we've complete mapping before this call. When we come down here to test our case, we know that we're going to be mapped. We haven't actually resolved ourselves yet for speculation. We know our outstanding mapping dependencies is 0. We know that we haven't called trigger resolution. So we're going to mark that we need to call trigger resolution. At that point, we're going to call trigger resolution. You'll see that we won't be complete yet because we haven't actually resolved our speculation case yet. But we are going to have our resolution ready to be resolved. So we call trigger resolution, jump back to actually go to operation, trigger resolution. It just turns around and calls resolve speculation. We go look at resolve speculation. You'll notice that he comes in here. We're going to take our lock. We're going to mark that we're resolved true. At this point, we will have mapped and executed, but we haven't actually completed our operation yet. So we can mark that trigger complete needs to be invoked. We mark that we need to trigger to true. So when we come down here, we're going to come down and hit this need trigger call. And then we're going to call trigger complete. you can see how we're progressing through the different stages of this operation pipeline. Operation, trigger complete. Notice that we don't actually do anything for this call. We just end up calling complete operation. We don't actually have to do much to complete this operation. So we call a complete operation. I know this is tedious, but it's useful, I think, to see all of the different stages that you progress through. Again, we're going to take our lock here, check all of our different states. At this point, when we call completed, we should already be mapped, executed, and resolved, but we shouldn't have completed. So we mark completed true. Now we check to see if we're actually safe to commit this task. There's a bunch of conditions here for actually testing whether or not it's safe to commit the operation, mostly dealing with whether or not we're actually running in a resilient mode where we actually need to wait to commit our operation in order to actually have it be safe and not going to have any rollbacks. In most cases, though, for right now, you can assume we're not running in resilient mode, so this condition will be true. We can ignore all of these other cases here. So at this point, we can mark trigger commit is true. We can mark that we need to trigger. We're going to get down here. We're going to call need. We know our need trigger has been set to true. We call trigger commit. For trigger, always forget to prefix this with operation. Trigger commit. At this point, we don't have to do anything again, so we call commit operation, and then we call deactivate. And deactivate is one of these virtual methods that actually do need to be defined for every operation class, and we'll see why that is a little later the next time. One important thing that you'll notice is that as we're progressing through all of these different stages, you'll notice that we can actually build a very large call stack. Because if you noticed, we just literally went through a whole bunch of function calls without returning. So you can actually progress through all of these different stages on one stack. And eventually, at some point, after you call deactivate, we're going to unwind all of these calls that get pushed onto the stack as you're progressing through all of these different stages. And of course, you don't have to progress through them all at one time. The base operation class, as I pointed out earlier, calls all of these complete and resolve operations right away because it doesn't have anything to do. But it's possible that, instead of calling complete mapping and complete execution here inside of trigger execution, what we're going to see is that there are other operations that actually go and launch meta tasks to actually do other analysis, or they actually launch our operation and don't actually call complete mapping or complete execution until the actual execution of an operation has actually occurred. So the depth to which you push these different stages onto your stack changes depending on the operation you're doing, as well as the actual analysis that's going on for each of these different operations. If you ever encounter, it's possible but unlikely that there is a bug possibly still in this operation logic. It's not out of the realm of question. We've definitely went through a fair number of them at the very beginning of getting this whole operation pipeline up and working. But it's been pretty stable now for, I'd say, about a year. So it's unlikely, I think, that you'll find any problems with this operation, the logic inside of these different operation classes. But if you do happen to come across one, try and capture a stack trace because it's really, really useful for debugging these kinds of problems, understanding the chains of events that can lead to having a race condition or something inside of the different stages of these operations triggering in different orders. So if you do ever happen across that, please let me know. It would be a very rare bug that it would be good to fix. But like I said, this logic has been pretty stable now for about a year, and I feel very confident that it's pretty much right at this point. Okay, so we're almost out of time for today, and I don't want to start anything new. So does anyone have any questions about the operation class and any of the logic that's going on here? The next time we're actually going to look in detail at some of the different operations that exist, and we'll go into some of these stages in more detail and see instances of them and how they're actually implemented for different kinds of operations, so that we can actually see some concrete examples of what we actually do for different actual operations that progress through this pipeline. And I guess it won't truly be next time. The next time Sean will be talking about the low runtime, but next Wednesday I will be talking about operations in more detail.
Mike?
Yeah.
Could you talk about the trigger execution call and why you call both complete mapping and complete execution in that one call instead of calling complete mapping in the trigger mapping call?
Yes, that's a good point. So what's actually going on, this is actually a good example of deferring the complete mapping call until we're actually done. And the idea here is we're actually adding this, by bouncing the trigger mapping call. Effectively, when we get this trigger mapping call, by bouncing the operation off of the local queue for the processor manager, by passing it, through the runtime to the processor manager, what we're getting is the effect of allowing the processor manager to figure out how to marshal resources for actually performing the mapping for this operation. And the idea is that we actually want to have the processor managers control how quickly things get pushed down onto the little runtime for actually doing work. And so we're effectively adding a level of indirection here to allow the processor managers the ability to control how operations get passed onto the little runtime. We could have just gone and launched ourselves right here in this trigger mapping call right onto the low level the low level runtime and actually done work. We could also have done work right here inside of this call and then call complete mapping. But the idea is that we actually try to break up some of the stages into smaller chunks so that we can not have low-level processors being consumed for large chunks of time. And so what we do is we add this level of indirection of bouncing operations off of the processor managers to control how much work is being put on the low runtime for meta-analysis at various points in time. So what we've done here is this is a great example, thanks for pointing out, Elliot, is that we've moved the complete mapping call into trigger execution to say that we actually haven't finished our mapping until we actually get trigger execution invoked by the low-level runtime or by the meta task that we launched to actually perform the execution of this operation. And what you'll see is that there's actually sort of the way to think about this is trigger mapping says that this operation is ready to map. And so what we do is we go tell the processor manager that we're ready to map. And then we won't actually map until we get called to execute. And when we get called to execute, what we'll do is we'll actually do the mapping and launch ourselves onto the low runtime. And we'll call complete mapping when we're done mapping. And for most of the operations, we won't even call complete execution inside of this trigger execution call. We actually really won't call complete execution until the actual operation itself has really completed or has actually completed executing. So the task is actually run or the copy is actually finished and so forth. And so that's effectively what's going on here and why these, complete mapping call actually shows up inside the trigger execution call and not in the actual trigger mapping call. Did that make any sense?
Yeah, I think that makes sense.
Yeah, it's a very, very flexible way of doing this programming, of having effectively this event-driven approach to programming, because you can do anything at any time and you can defer things as long as you want. Getting the logic right is very hard, but I've hopefully abstracted a lot of the details of this logic inside of this operation base class so that we don't need to modify it ever again, or it shouldn't need to change in the future. Okay. Well, anyone have any more questions? If not, I think we're done. All right, Elliot, I say we're done for today.
Mike, can you give me a quick phone call after this?
Yes, I will.
Thanks.